Okay, so let's get a look at those liver lobules. And kind of honeycomb looking with the hexagonal shape. The central vein they were talking about is right there. But what I want you to notice, if we could zoom in better, and we can't on this slide, but if we could zoom in, at each corner we have that portal triad that the previous slide was talking about, where it says that each corner of a lobule contains a hepatic artery, a hepatic portal vein, and a bile duct. And so the artery, of course, is bringing the oxygen. The portal vein is bringing nutrient-filled blood from the intestines, and the bile duct is receiving bile canaliculi, is bringing bile from bile canaliculi, which has the fat-filled bile. So all of that stuff is going to the liver. All right. Oh, there's a nice zoom in. Okay. So the central vein, and if you look, you see these spaces, these sinusoids, as the blood has to percolate through there, all of the cells that's going by, all the hepatocytes, they are looking for things that don't belong and trying to kill them out, kill it or take it out. What you're seeing right here, that vessel, that vessel, that vessel, those are the portal triad. So, and you can see again a group of 3 right there in each corner usually. Okay, so the microscopic anatomy of the liver. The sinusoids are those spaces, leaky capillaries running between the plates. And the blood from the hepatic portal vein and the hepatic artery will percolate through these triad regions, through the sinusoids, and empty into that central vein. Now, stellate macrophages, hepatic macrophages in the sinusoids remove debris and old red blood cells. Um, I think unless they're separate from the other macrophages, those used to be called Kupffer cells, but we'll move on. We'll move on to be sure. Anyway, you have macrophages that live in the edges. So here is a nice blown up diagram of what you're seeing. And so if blood arrives through at the corner through the portal triad, it has to go through between the plates of hepatocytes before it gets to this central vein where it can be drained off. All right. So hepatocytes have a lot of ER, rough ER, smooth ER, a lot of Golgi apparatus. What that's telling you is they're making a lot of stuff. A lot of peroxisomes, a lot of mitochondria. So they're using a lot of energy. They're making a lot of stuff. And peroxisomes tells you they're trying to kill a lot of stuff too, or neutralize a lot of stuff. The hepatocytes are going to make about 900 milliliters of bile every day. Compare that to the saliva. They're doing more than the saliva. So more than the salivary glands do saliva. They process bloodborne nutrients. So say you have glucose in the blood, they're going to turn that into glycogen. They're going to take amino acids that are coming by and turn them into the plasma proteins, things like albumin, things like, oh God, why can I not think of it? Anyway, but yeah, turn them into plasma proteins. And this will also store the fat-soluble vitamins. That's A, D, E, and K, vitamin A, vitamin D, vitamin E, vitamin K. And they will detoxify chemicals. So like if there's ammonia in that blood that's floating by, they'll turn it into urea, which is less toxic. They'll also try to neutralize alcohol, like I said. Okay, bile composition and enterohepatic circulation. So you have this yellow-green, bile is a yellow-green kind of stuff. It's alkaline, it's basic. Bile salts are made out of 2 things. bile is made out of two things: bile salts, which are cholesterol, pieces of cholesterol that do fat emulsification, taking the big drop of fat and breaking it into lots of little droplets, so there's more surface area for the lipid digesting enzymes to work on. And then the other part is bilirubin, which is formed from the breakdown of heme. So when the spleen is breaking down the red blood cells, and I told you that the heme, because it has the iron, is precious. We're going to keep that. Well, the rest of that heme you're going to break down. You dump the bile into the duodenum, the small intestine, and the bile salts will do the emulsification, make it easier to digest the fats. The bilirubin will encounter bacteria that will turn into stercobilin, and that stercobilin is the brown stuff that makes poop brown. There also in the bile are cholesterol, triglycerides, some phospholipids, some electrolytes. Okay, so let's talk about enterohepatic circulation. There's a recycling mechanism that conserves bile salts. So bile salts are reabsorbed into the blood by the ileum. You remember the small intestine is divided into the duodenum, which is right by the stomach, the jejunum, which is the curly, sausage coily looking part in the middle, and then the ileum is the third part, the end, the one that ends at the ileocecal valve to go into the large intestine. Well, that last part of the large intestine, the ileum, it reabsorbs the salts and it returns them to the liver through hepatic portal blood, and then it's used to make new bile. Only about 5% of new bile salts need to be made. We recycle 95% of it. But the bilirubin that turns into the stercobilin, we just get rid of that. We just poop that out. All right, so here we have the circulation. And wow, it's everything that we said in the previous slide. All right, so let's talk about homeostatic imbalance in the liver. Hepatitis, inflammation of the liver, usually caused by a liver infection. Could also be caused by wild mushroom poisoning or drug toxicity. Cirrhosis is inflammation of the chronic inflammation from long-term hepatitis or from alcoholism. It takes the liver and makes it fatty and fibrous, and it causes portal hypertension. If someone has this, you could do a liver transplant if you could find a liver, but they're hard to find. If you remove a lot of the liver but leave some behind and then live a healthy lifestyle, it could grow back. So it could grow back to its full size, according to this, in 6 to 12 months after 80% of it was removed, which is amazing. If only we could do that to all our other organs and organ systems. Anyway, the gallbladder, thin-walled muscular sac on the bottom of the liver. It stores and concentrates the bile. It does this by absorbing out the water and the ions. Lots of honeycomb folds that let it expand as it fills. Remember the cactus example. Remember the rugae in the stomach. Muscular contractions will release bile through the cystic duct, which flows into the bile duct. All right, so, oh, great. Now we get to talk about gallstones. Ew. All right, you got too much cholesterol and not enough bile salts, you can form stones. They can obstruct the flow of bile from the gallbladder. They're painful. You got sharp-edged crystals, and the muscles trying to squeeze and it's getting poked by the crystals. If the stones are big enough to actually block the flow of bile, then you can get obstructive jaundice. The bile salts and the pigments will build up in the blood, and then the skin will turn yellow. But this could also be caused by liver failure. So if your skin's going yellow, the doctor is probably going to freak out, and you should too. So how do we treat gallstones? You could take drugs that'll try to dissolve the crystal. They could do ultrasound lithotripsy, where people go in the water and they aim sound at it to pulverize them. I had a friend that they did that to for kidney stones, and it was the treatment itself was not too horrible, but passing the jagged edged fragments of the stones later was not fun. Anyway, you could try to use lasers to vaporize it, or surgery to extract them if you have to. All right, now we talk about the pancreas. It is mostly retroperitoneal. That means it is behind the peritoneum. It is behind that parietal serous membrane, at least partially. It's below. It's deep to the greater curvature of the stomach. The head is encircled by the duodenum of the intestine. The tail is by the spleen. Exocrine function. So it produces pancreatic juice. This is what we're excreting. The acini are clusters of cells that make zymogen granules, and those zymogen, these little grains have proenzymes in them. Fancy way of saying future enzymes, things that will take on their proper shape when they're exposed to the right chemicals. They also have ducts. The pancreas has ducts that will squirt into the duodenum via the main pancreatic duct. Smaller duct cells, these are making water and bicarbonate. Remember, I told you that the chyme would attack and destroy cells in the duodenum, the first part of the intestine, if we didn't find a way to neutralize it. Well, this is how we neutralize it. We have bicarbonate-rich fluid coming out of the pancreas through the pancreatic duct. Oh, and then there's the function that everyone knows about that's super famous. The pancreas has endocrine functions. It's supposed to make insulin and glucagon. And this is done in pancreatic islet cells. I'm used to the older term, the islets of Langerhans. You might hear me use it both ways, so don't be scared if you see islets of Langerhans. We're talking about pancreatic islet cells. All right, so here we have enzyme-producing tissues in the pancreas. Not talking about hormone-producing. So the acinar cells, they make the enzymes. They're making them in little zymogen granules. And we have, in order for them to do that, lots of rough ER because they're making proteins, enzymes. Lots of mitochondria for energy to do their job. A basement membrane that holds everything together. And then a little duct that all those granules are going to come out of. All right, so that's cool. And here's the actual histology slide. So same deal. Composition of pancreatic juice. You're going to make maybe up to 1.5 liters, 1,200 cc's to 1,500 cc's a day. It's watery, it's alkaline, not strongly alkaline, but pH 8. A heck of a lot better than stomach acid at pH 2. That'll neutralize the acidic chyme coming from the stomach. And it's full of electrolytes, especially bicarbonate from the carbonic acid. It's full of digestive enzymes. This includes proteases that'll break down proteins. These are secreted in an inactive form, so they won't eat the pancreas. but when they hit the duodenum, they're activated by the pH change. There's pancreatic amylase to break down carbs. There's pancreatic lipase to break down the lipids. There are nucleases to break down the nucleic acids. What I'm saying is all four of the major macromolecules in nutrition, you are secreting enzymes to break them down in the duodenum. So this goes back to that, hey, you know, the duodenum is the main digestive organ, small intestine. Actually, small intestine is duodenum, jejunum, ileum. But most of the breakdown is in the duodenum. All right, so let's move that. So the dog who just jumped on my lap does not steal the plate. Okay. Pancreatic juice, more on pancreatic juice. The proteases are secreted in an inactive form. Yeah, we understood that. They're activated when they hit the duodenum. Enteropeptidase is an enzyme that is, wrong direction, that is bound to the plasma membrane, the outside membrane of the duodenal epithelial cells. A lot of these we call brush border enzymes. But yeah, they're enzymes that are in the outer membrane on the epithelial cells. And what does this enteropeptidase do? It activates the pancreatic trypsinogen, turns it into trypsin. Trypsin is capable of doing more trypsinogen, and it can turn procarboxypeptidase into carboxypeptidase. It can turn chymotrypsin into trypsin. What we're doing with the trypsinogen, trypsin and chymotrypsin are protein digesting enzymes. And although I don't know carboxypeptidase well, the fact that it says peptide in the middle means it works on amino acid chain. So again, we've got three different enzymes for digesting proteins that are being released into the small intestine. All right, there you go. I would say I want you to know those three enzymes. The path of which one activates which one, not so important. I do want you to know that if you see OGen, that is the inactive form. So know that trypsinogen is inactive and trypsin is the active digesting form. Pro means before. So know that procarboxypeptidase is the inactive form that is turned into that comes before. Will be turned into the carboxypeptidase. And the same thing, chymotrypsinogen, how do you know that's inactive? Because it says OGen. Like will generate, and that becomes chymotrypsin. Okay. So the bile duct and the pancreatic duct unite in the wall of the duodenum, and they fuse together into a little structure that sticks in a little bulb-looking thing called the hepatopancreatic ampullae. So this ampulla, it opens up into the duodenum, volcano-shaped. Okay, I would have thought more of a giant pimple, but whatever. Volcano-shaped major duodenal papilla. In other words, that's where all the stuff comes in. The hepatopancreatic sphincter controls bile and pancreatic juice going into the duodenum. The accessory pancreatic duct, it's a smaller duct that empties directly into the duodenum. So that exists too. It doesn't hurt to know that that exists too, but I want you to definitely know the main one, the hepatopancreatic ampulla. All right. So there we have the papilla that we were just talking about in the wall. All right, how do we regulate this? Bile and pancreatic juice are stimulated by neural and hormonal controls. The hormones could be cholecystokinin or secretin. Secretin tells you to secrete stuff. I don't have a good mnemonic for cholecystokinin. Anyway, bile secretion is increased when large amounts of bile salts are being returned. Secretin from the intestinal cells is exposed to hydrochloric acid and fatty chyme. In other words, we're squirting things through the pyloric sphincter. That will stimulate the gallbladder to release bile. If the hepatopancreatic sphincter is closed, it is closed unless we're doing digestion. Bile is stored in the gallbladder and released to the small intestine only when we contract the bladder, the gallbladder. All right. Again, this picture says the same things we've been saying. Oh, and that is the end of. I know this is the third part that we recorded, but that is the end of the part 2 of the PowerPoint. All right. So let's wrap this up. And yeah, I know screen sharing has stopped. Calm. All right.